Okay, so yesterday we talked about confidence intervals, two proportions, right? So when we talk about two proportions or two samples, our question is, are the two samples significantly different? Okay, so the sample versus the sample, not what we saw in chapter 8, chapter 9, which was, is our one sample different from what's claimed? Okay, that's just a little review of yesterday. Okay, so we did talked about intervals yesterday. Today we're talking about tests. Today we have a two proportion z-test. Okay, same idea as yesterday, except we're testing a claim as opposed to predicting or estimating the difference. We're testing a claim. The claim is always going to be the same for two samples. The samples are the same. Okay, there's no significant difference between the two samples. That'll always be the null. So when testing the hypotheses that there is no significant difference or no significant change between the population proportions, okay, that'll always be. So we'll always have a null hypothesis of proportion 1 is equal to proportion 2. That'll always be our null hypothesis. Of course, we won't write 1 and 2. We'll change it like we did yesterday, NV, NP. But that's essentially what it means. That'll always be for two sample proportion tests for this test. Okay, the null will always be no difference. Okay, parameters and assumptions are the same as yesterday. So these guys right here, same as yesterday. Okay, the key difference here is we got to do something called pooling. Okay, we only pool today. We only pool on two proportion tests. Everything else we do not pool. Okay, so today we're going to do something called pooling. That's only a today thing. It never, ever, ever, ever occurs outside of this test right here. Okay, never, ever occurs. So when we do that, just know that it only goes with this test. It doesn't go with another interval. It doesn't go with another test. It only goes with this test. Okay, and again, these are very popular on the FRQ section. Okay, two sample. They love two sample. They love comparing samples on that. Okay, our test statistic is, again, it's bigger because we have two samples, right? It's bigger. It's a bigger formula. But if you actually dive into it, it's just the same formula twice, right? That formula we have on our sheet. This we did yesterday, right? Subtract p hat 1 minus p hat 2, right? So it's not too bad, especially because this part right here, I think this part right here might actually be on the, look at the back of your, Aldrin, look at the back of your, is this actually, can you find this anywhere?
The PC?
No, just this guy right here.
Yeah, right here.
It's actually right there, the whole thing, right? So the whole thing's actually there. They just don't give you this. Okay, and you know it's always Z because it's, that's the one, yeah. Okay, this is the pooling part. So you can kind of understand what pooling is. I'm going to explain when we get to the actual question, I'll explain why we pool, but this is how we do it. So you see all these p hat C's, all of these are going to be calculated by doing this. We take the number in the numerator for the first sample, add it to the numerator in the second sample, divide it by the number in the denominator for the first sample plus the denominator in the second sample. That's pooling. We pool the samples together, and I'll explain why we do that when we actually get to the question. But that's all it is. Okay, it's not hard. It's just remembering to do it. Okay, and your calculator will always ask you, do you want to pool? For this, yes. Everything else, no. Okay, and the conclusion's the same. All right, so let's jump ahead. Let's jump ahead to the problem. It's the last example, I believe. Researchers designed a study. Okay. Researchers designed a study to compare the proportion of students who come to school without eating breakfast among the freshman and sophomore classes at Central High School West Campus. An SRS of 80 students from the sophomore class found that 19 of them missed breakfast that day that they asked. An SRS of 150 students from the freshman class included 26 who missed breakfast that day. There are more than 1,600 students who attended Central High School West Campus. Do these data give convincing evidence of a difference in the population proportions? Okay, so we have two samples. We got a sample of sophomores and we got a sample of freshmen. All right. So again, we can use p hat 1, p hat 2, but then we'd have to label what 1 and 2 are. So instead of p hat 1 and p hat 2, what should we do?
P hat sophomore, P hat freshman.
Exactly. P hat S, P hat F. That works. So p hat sophomores. What is the p hat? 19 out of 80, which is a little less than 0.25. Wait, 19 divided by 80, 0.238. P hat freshman is 26 out of 150, which is repeating. Okay. They're going to ask us later on for x1, x2, n1, n2. What are those numbers going to be?
Doesn't matter.
Well, what is n1 and n2? What are they? Sample sizes, and what's x1 and x2? Because I always get this question. What is x1? That's the numerator. Okay. So if you don't want to write it down, just know that when it's calculator time. Okay. Let's see. Anything else? Significance levels 5%. That's about it.
Or the hypothesis.
Yeah. So anything else before we get into the actual test? All right. So let's get to the test then. So population proportions, population parameter. We have two of them. We have PS and we have PF. So we have P hat S. So P hat S is a sample from the bigger group. So who is the bigger group represent? True proportion of sophomores who missed breakfast. Yeah. Who missed breakfast. Okay. PF is very similar. Again, you can write it word for word, or you can use the quotations. The only word that changes is freshman. Okay. Hypotheses. Now hypotheses. So it's a two proportion test. So anytime we have a two proportion test, the null hypothesis will always be the same. P hat S equals P hat, or sorry, not P hat, P. We don't put P hats for hypotheses. We only put P or mu. So that's one way to write it. So you might also see this. I'm going to write it a different way. So you might also see it like this. It means the same thing, but I want to show you since it might come up. Do those mean the same thing? They mean the same thing. They're equal, right? The second one just says if I subtract them, I get the same number. I get 0. That means they're equal, right? That's no different. So I don't care which one you write. I don't care if you write this one or this one. But if you're doing a question and they give you one and it looks like that, you know what it is. Okay. Okay, so our our alternative hypothesis. So yeah, let's go back. Is there any wording?
Do these data give convincing evidence of a difference?
Difference. Yep, just different. So it doesn't say greater than or less than. So we would say not equal to. Again, another way of writing it that you might see is this. You don't have to have both, but I'm just writing it just so that if you do see it, you know what it means. It's another way of saying the same exact thing. Okay. So there are sometimes a question. They'll ask you some questions. I think they've asked you on the homework. They'll say, does your p hat, does your sample lead you to a certain alternative hypothesis, or does it give you any kind of insight? Okay. I haven't asked you that on a test, but it might come up. So when they ask that kind of question, you always look at your p hats. Well, based on our p hats, there is a little bit of a difference. Is it significant? I don't know, but there is a difference, right? 0.238 and 0.173. Is that a big enough difference to be significant? I don't know. I got to continue going with the test. But if they were asking me, is there any insight? Well, I would just say the sample proportion of sophomores is a higher proportion of missed breakfast than freshmen. So that might be something. But so sometimes they might ask you that because I've noticed they will throw that in sometimes too. If they just want you to take a look at before you actually run the test, what are you looking at? That's all they're saying. Okay. Alpha level, 5%. Okay. Test statistic. Okay, so test statistic. We're going to use, so we're going to say p hat s minus p hat f on top. On bottom, we're going to say ns, so p hat, not s. Wait, is it s? Let me see, go back. Yes, N1, N2. The rest are PCs. Okay. Plus p hat c 1 minus p hat c over nf. Take the square root of that guy. Okay. That defines what test we're using. That's our label for what test we're using. Okay. Next step, conditions, assumptions. So we have our 3 conditions. I have 2 samples to test, to check. So the first one is going to be a check for P S, and then the next one's a check for P F. So, okay. Number 2, 10% condition. So n is less than 10% of big N. Okay. So for PS, what was N? 80? Okay, is less than 10%. And what number or who is big N? 1,600. They actually give us the population number, right? 1,600. This one was, what was 150? Yeah, because this one's going to be 160, right? And the other one is going to be barely. But it works. So it's almost too big. Okay, last one is normality. So we have NP greater than or equal to 10 and 1 minus P greater than or equal to 10. Okay, so let's see, N. We don't have P, so we're just going to use the P hat. So P hat for sophomores. 238. Okay. And then 1 minus 0.238. Then over here is 150 times 0.173. And then 150 times 1 minus 173. They all check out. They're all bigger than or greater than or equal to 10. So they're big enough, but not too big. Number 2 is too big. Number 3 is big enough. Okay. All righty. Next one, we have calculations now. Okay, calculations. All right. So when we actually use our formula here, right, we're going to need PC now. So we got to calculate PC. Okay. So this is where we do the pooling. Pooling, like I told you guys before, it's add the numerators, add the denominators. So if we add the numerators, we get 19 plus 26. If we add the denominators, we get 80 plus 150. So that's 230 on the bottom over was that 40, 45? Yep. Which is 0.196. That's our PC. The reason we do that, why do we pool for proportion tests, is because what do you notice about the two sample sizes between freshmen and sophomores? There's a difference. Is it a big difference? Relatively speaking. Well, relatively speaking, is it bigger?
Yeah.
Yeah, it's almost double, right? So because this sample was done back in the old West Campus days, but when we were West Campus and we had majority freshmen, so that's why the sample was bigger, right? So we didn't want to. So the reason we pool the two samples together is because we don't want one proportion to over dilute the results. So we put them together. We pooled them. Okay. So now this proportion represents both. Okay. That takes care of that. That's why we do it. Okay. Because one sample size is almost double the other one. So we don't want that one to what's the word? Overshadow, overcook what's actually going on. Okay. So that's why we pool. 0.196 represents both. Okay. All right. So on top we got p hat for sophomores. P hat for sophomores was 0.238 minus 173. Good. Down here, we're going to use P, they pooled P. We still need the sample size here. So sample size for sophomores was 80. And then the sample size for freshmen was 150. Okay, so what's the mean? Here's another question. What's the middle going to represent? How do I figure out what is the middle and how do I figure it out? No, that wasn't the middle. What are we testing here? What's the key word in what we're testing? Not equal. It's a word. It's one word. We saw it yesterday too. What is the one word that yesterday's example and today's example have in it?
Different?
There you go. The difference, right? It's the difference we're concerned with. It's the difference. So what is the claim difference? 0. So that's going to be in the middle here. Now, based off our sample, what is the difference?
Oh, 0.196.
No, that's not the difference. That's pooled. What's the difference in our sample proportions?
That is
0.238 minus 173. 0.238 minus 173. You get 0.065. That's what I'm going to. Which way do I shade?
the nose.
Towards the tails. Yep. Why do I shade towards the tails? You're right.
Because we're trying to find the difference. Or we're trying to prove that they're different.
Yeah, but why do I shade the tails instead of the other way? Where do I look? In other words, where do I look when I want to know which way to shade? Where do I always look? Where have we always looked when we want to know which way to shade? The alternative hypothesis. And what did the alternative hypothesis say?
Different? The two proportions are different? Or the two samples are different?
So my question is, why did I shade right? Exactly. So I'm missing a bunch, right? That's just half of the shaded area. The other half is over here. So this distance is 0.065. I need one in the opposite direction. So it's just going to be the same, just negative. And I shade towards the extremes again. Okay. Your calculator will do all of this for you. We'll calculate both blue sections for you. But I mean, you saw on the test when we took it that sometimes you need to calculate it on your own. You need to use the table, right? So the table will give you one of the blues. You got to double it. The calculator will give you both. So it just depends on what you use. Okay. All right. So let's use the calculator. We'll use the calculator and then we'll use the table. I'll show you how to use the table. You probably already know how to, but we'll go over it just in case. So let's get out the calculator. Okay, so if you got your calculator while I'm waiting for mine, go find the test. Go find the test we are going to test. Which test out of the list of tests and intervals are we going to use? We're slowly whittling them down. We have a couple more left. But it's one of the ones we have not used yet. Let's see. So we need a 2 in front, and I need a proportions and a test, right? So which number is that? 6. There we go. Okay. So the top number, X bar 1 or X1, what was X1? X1 represented sophomores. So that's going to be 19, 80, and then 26 over 150, not equal to. Calculator draw, doesn't matter which one you use because they're both going to be the same, or they're both going to give you the same information. So the first one underneath the not equal to, underneath the alternative hypothesis is your z-score. So we got to write down the z-score. 1.17. The p-value for both is right underneath that. 0.2427. So the first number is the alternative hypothesis. The second one's the z-score. The next one after that is the p-value with both added up. Both of those guys are added up. And then the rest we already had. Okay. Okay, so now before we go on, how do we do it using the tables? So if I want to find the p-value using a table, first of all, which one am I going to use, z or t? I'm going to use z because it's proportions, right? So let me get my z-score tables out. Z. Okay. How do I do it? I got my table in front of me. Where do I look? Look at my z-score. I got to find my z-score first, right? So my z-score is 1.17. Okay, so I'm going to go to 1.17. 1.17, did I say?
Yeah.
117.
Oh, 1.17.
Right there? 1.17? 0.8790? Okay. So what does that represent? Because I didn't get that. How does that help me find area in the blue? How does that?
Subtract that by 1.
There you go.
Then you multiply by 2.
Subtract it by 1. So if I subtract it by 1, 1 minus, why do I keep doing that? 1 minus 0.8790 is 0.121. That is the area of one of the blues. Double that, and I get the area 242. Okay? Because on multiple choice questions, they will have you use the table instead. They'll give you key parts of information. They'll give you the z-score. They'll give you the alternative, and they'll give you the null hypotheses. And then they'll say, what is the p-value? You can't use the calculator because you don't have enough information, right? Wait, go back to the calculator. Go back to the calculator. 1 second. Let's go back to what we just did. Let's go back to the one we were at, just at. They didn't ask you for pooling, right? Does anyone have a calculator that asks for pooling? That's weird. That's weird. They didn't ask you for pooling. Usually what they'll do is they'll ask you for pooling. They'll have another one of these guys and they'll say click yes or no for pooling. Okay? So I guess they automatically just assume we're going to pool.
I mean, there's no situation where you wouldn't pool it.
Nope, not in this case. Oh, they do give us the pooled one. The one below p hat 2, 196. That's our pooled one, right? 196. They just must have changed since the last time I looked at it. They must have changed the updated the software, so they just put that automatically in there. They don't make you choose whether you want to pool or not. Okay. All right, so let's finish. Okay, so first thing, compare p-value with alpha level. Since p-value 0.2427 is it greater than or less than our alpha? Greater than alpha. What do we do? Reject, fail to reject. Fail to reject. Reject the null hypothesis. Therefore, we do or do not have sufficient evidence? Do not. This last part can be a little tricky. To suggest sufficient evidence.
Suggest that the two samples are statistically different.
Yep. We want to be a little more clear though with the samples. Instead of saying the samples, we want to say what the samples are. So who are the part of the sample? But yeah, essentially you're right. To show or to suggest the true proportion of sophomores who miss lunch or miss breakfast is significantly different than freshmen. Essentially what you said, Aldrin, just in context. So the two samples we use sophomores and freshmen who miss lunch. Therefore, we do not have sufficient evidence to suggest that the true proportion of sophomores who miss breakfast is significantly different than freshmen. Even though the samples are different, they're not significantly different so that I can say that for all students at Central West High School, right? I can only say they're different for the samples, but I don't care about the samples. I want to be able to tell about the entire population. Exactly. I want to be able to generalize it. That's my goal. Okay. It's easy to take samples, but the reason we take samples is to generalize about the population, right? If I want to know who's going to win an election, I'm only going to take a sample of people who can vote. I'm not going to take a sample of people who can't vote because that won't be able to generalize the population. Okay. Okay. I don't know if we're going to finish the next section, but we can at least start on it. So we skip some parts. Same notes. I'm not going to give you extra notes, but go to this one here, the green one. It's not green on your paper, but it looks like this. It's shaded. We've done kind of this stuff before. Sampling distribution. We haven't really talked about sampling distribution in a couple chapters, but we've talked about it before. So if they ask you about the sampling distribution for the two samples, the difference in the two samples, this is what we're going to do. This is how we tell. Okay. The sampling distribution is approximately normal if the large counts condition is met, normality condition. The mean is you just subtract them, and that's the mean difference. That's the mean difference, right? So when they say the mean of the sampling distribution, they're just talking about the difference. And then the standard deviation, that looks familiar there. We just did that, right? Except you don't have to use the pooled one. You use a P1 and P2 or P hat 1 and P hat 2. Okay? Yeah. Yeah, this one is on your sheet. On your, literally written like just like that on the sheet, right?
Yeah.
Okay. Yep. Okay. Okay, so last thing I want you to do, answer those three questions.